Let's take a look at another example here. In a previous example, we looked at y equals x plus 1 from y equals 0 and y equals x about the y-axis on 0 to 1. And we broke it down like this, and we came up with 5 pi over 3. But we had to break this thing down in order to do it. Let me draw a quick picture of what I'm talking about here in case you forgot which problem this was. X plus 1 like this. X-axis, y-axis, and we revolve this thing around the y-axis like this. And we're looking for this solid. And when we did it, we said, well, gosh, I need to break it up into this half and then this upper half, which is represented by these two different integrals, in order to get that 5 pi over 3. But the nice thing about the shell method is I could do this exact same thing all in one shot. So if I'm revolving about the y-axis, then my representative rectangle is going to look like this. This is what I'm going to be spinning around. So P is going to go from the axis of revolution to the center of the rectangle. And the height of this rectangle is just going to be this function minus 0. So P of x is just going to be x. And h of x, the height of that rectangle, is just going to be x plus 1. So that means that my volume equals 2 pi times the integral from 0 to, this came out to 1, from 0 to 1 of x times x plus 1 dx, which is just going to be 2 pi times the integral from 0 to 1 of x squared plus x dx. So that's going to be 2 pi times x cubed over 3 plus x squared over 2. Evaluate from 0 to 1. The 0 is nice. I like that. So this is going to be 2 pi times 1/3 plus 1/2. So this is going to be 2 pi times, this will be 2 plus 3 over 6. That's 5/6. That'll cancel. That's 3. And so that is 5 pi over 3. So we got there, the same answer, without having to break this down, because we recognize these functions are nice with the shell method. All I have is a top and a bottom, and that P is just simply x. So it drops out very, very nicely rather than having to, like I said, break this into two separate situations and work with it from there. So let's go on to another example here. I want to take a look at the exact same situation, same function. On this time, I want to revolve it around x equals 1. Well, what does that mean? Well, I have this function here. It comes out to 1. But this is now going to be my axis of revolution. I'm not going to revolve it around the y-axis. I'm going to revolve it around this thing. So when I do, what I get is something that looks like this. And this is the solid that I'm looking for. Well, my representative rectangle is going to look like this. So h of x really hasn't changed. That's just going to be x plus 1. Now, p of x has definitely changed, because I'm going, rather than from the y-axis to here, I'm going from the axis of revolution, 1, to here. So how do I represent that? It's no longer just x. So this distance, as x goes from 0 to 1, this distance will be 1 minus x. So that gives me a volume of 2 pi times the integral, I'm going from 0 to 1, of x plus 1 times 1 minus x dx. Multiply this out. I won't take any shortcuts. I'll do it all for you. This is going to be x minus x squared plus 1 minus x dx. Just expand that. See, these x's go away. So I'm going to end up with 2 pi times the integral from 0 to 1 of negative x squared plus 1 dx, which gives me, 2 pi times, this is negative x squared over, Sorry, I didn't integrate that right. Wrong antiderivative. This is a negative x cubed over 3 plus x, value from 0 to 1. So this is 2 pi times negative 1/3 plus 1 minus 0. So this is a 2/3. This is 2 pi times 2/3, which is 4 pi over 3. Again, the units, we don't specify what we're working in, but it is cubic something.